are given a equals p1 plus r over n raised to nt. This will be given to you. This is the interest compounded n times per year. Okay. We are given that the amount invested, which is the principal, is 5,000. We are told that the accumulated amount is 9,000. Now, the correct model should be A of t. T is the variable in the problem. R is a constant, N is a constant, P is a constant. So it should be clearly stated by the book. For some reason, they don't. Okay. Number of compounding periods, 365. We are told this is 365. And we are given the interest rate, which in this case is 14.7. I have to change it into 0.147. 14.7. Now I will replace everything. 9,000 equals 5,000. 1 plus 0.147 over 365 raised to 365t. Are we okay so far? So we have all the information, we put it in, and now what is the only variable here? All our numbers, the only variable is t. Okay. So obviously it's an exponential equation because the variable is not here, but here, right? So it must be exponential. Perfect. How do I clean it up? Always keep this in mind. If you just learn this from this class, I'm happy. Factor, simplify. Always you should have those two in the back of your mind. So, by? Absolutely. Thank you. 9/5 equals 1 plus 0.147 over 365 raised to 365t. Yes, you can simplify this and come up with a number. Don't. There is no need to do anything here. Yes, I know we can use the calculator and add 1 plus 0.147 over 365. Don't worry about it. Now, this is completely cleaned up, and the variable is at the exponent. What should I do? Apply a mechanism that undoes the power. Undoes the power. Yes. So I have to apply natural log. So the inverse function of the exponential is log. The inverse function of this function of the square root is square both sides. The inverse function of power 2 is the square root.
Do you have to use natural log or can you use log too?
It doesn't matter. Yes, but I would prefer to use one that I have in the calculator.
Right.
My calculator is not sophisticated. It doesn't allow me to plug in any base I want.
Right.
So I should use either ln or log. Okay. The reason I use ln is because it's easier to write than log, but it doesn't matter. You can use either one. As long as you apply the same function to both sides, you're safe. You cannot apply log to this side and ln to this side.
But E is ln.
E, yes, the e to the x is the inverse of ln x. Yes. Very good. So which one would you like to apply? It doesn't matter. Okay. So natural log 9/5 equals 365t multiplied by natural log by this weird number I don't care about, 0.147 over 365. Now this is a tremendous important step because now I know how to solve. This is linear now. I have t and then it's multiplied by these two numbers. One more time, do not ever get impressed or scared by this. This is just a number. It looks sophisticated, but it's just a poor, simple number. So I'm solving for t, obviously dividing by these two quantities. And the top is natural log 9/5. So the function that takes care of the power or eliminates the power is natural log. Now this I have to put in the graphing calculator. So we are ready now to put it in. So we had natural log 9 divided by 5, close the parenthesis, divide by, in parentheses. This is extremely important.
Yeah.
Although you have a product in there, if you don't put parentheses, the calculator will divide only by 365 and multiply the entire answer by natural log. And this is not what we want, right? So that's why we need parentheses around the denominator. 365 multiplied by natural log, and in parentheses we have 1 plus 0.147 divided by 365. Close the parenthesis, and don't forget to close one more parenthesis for the outside of the denominator. If you omit this, the calculator will divide that by 365 and multiply the answer by this, by the natural log. So now we press enter, and we get 3.999. So what does that mean? It's time in years. What would you say?
That's about 4 years.
Exactly. Is that clear? So T approximately 4 years. Is it difficult to check? No. Here's how you check. You multiply 5,000 by this raised to 365 times. What should the answer be? Right. You can always go back and check. Good. Very good question. Thank you, Wendy. Is this clear now? Any questions? Is there anything else that you would like to go back to? Is there anything else? So we only looked at logistic growth model. We did not look at the exponential growth or exponential decay. So now this is the time. Yes?
Can we go over something I did on my math file?
Yes, anything.
Okay.
Yes, of course.
So it's 1 over 8 bracket.
1 over 8
Yeah,
bracket here.
Yeah. 5 natural log, parentheses, x plus 9, minus natural log, x, minus natural log, parentheses, x squared minus 36.
Like this?
Yeah.
Perfect. So therefore, 1 over 8 will wait patiently. I see this is a clean natural log with minus in front, clean natural log with minus in front, but not clean natural log because it has a 5. Where does this 5 come from? Yes, right here. So that will be my first step. Natural log x plus 9 to the 5th power minus natural log x minus natural log x squared minus 36. Now we discussed that log that has positive in front, its quantity is coming from the numerator. And log that has negative in front, its expression will come from the correct. So this is 1 over 8 natural log x plus 9 to the 5th over x times x squared minus 36. Is this okay so far? Is this okay? Final step, I need to get rid of this. How do I get rid of this? This is the power of the whole thing. But what power is 1/8? Power 1 over 8. The 8th root of x plus 9 to the 5th over x squared minus 36. Power 1 over 8 is the 8th root. Power 1/2 is the square root. Power 1/3 is the cube root. Is this better? Good. Other questions? So that's all we were asked to do. We were asked to condense this sophisticated, if you want, long expression of logs into one log with coefficient 1. If there is anything else in front, I have to make it the power of the quantity. Very good question. Thank you for that. Thank you, both of you. Anything else? Other questions? Anything else that you worked on? Anything else you worked on? Okay, then, so let's look at the exponential decay and exponential growth. Do we remember this formula? I'm not asking you to, but do you remember seeing it? It should have been the correct model, should be A of t. P is a principal, E is a number, R is a number, T is the variable. This was the compound interest, continuously compound interest, right? Continuously compound interest. A of t equals A0 e to kt. And the other one, A of t equals A0 or A naught e to negative kt. Do you see any resemblance among these three? No, this was a positive. It has positive in front of k. This one has negative in front of k. But do we see the resemblance? There is some number in front in all three. There is the base of e, same thing in all three. There is t, which is time in all three. And there is r, k, and negative k, right? So we see a lot of resemblance here, correct? Okay, so these two are the growth models. This one, the exponential growth. And this one, the exponential, what do you think? That's it. The first one is for populations, birds, fish, you name it, bacteria. And the second one is for radioactive substances. Okay, this one will be an increasing, that's why we call it growth. This other one will be 1 over e to kt, so it will be decreasing. And they're all pretty much the same thing. It's just that here, this is amount and this is money, principal, annual interest rate, time in years. This is the amount of bacteria, the initial amount or population, the growth rate and time. This one will be the mass at time t, the initial mass, time in years, and k, the decay rate. They're pretty similar, all three. Okay, so let's start with the exponential growth, and let's look at a few word problems. Okay, we are on page 529. Are we interested in problem 7, which deals with population of Israel, problem 8, which deals with population of the Palestinians, and then 15, 16, which will be the exponential decay. So let's choose. Israel. Okay, so let's look at problem 7 then. 7 on page 529. And let's read the problem. In the year 2000, the population of Israel was approximately 6.04. 2000, 6.04 million. In 2050, it is projected to grow to 10. I'm just reading the problem and taking notes at this point. Use the exponential growth model. This will be given to you, and I will correct this model. My math lab uses a. It's a of t. It's a function that is clearly a function of time, not anything else. Is a0 e to kt, in which t is the number of years after 2000. T, number of years after 2000, which means t equals what for 2000 then? 0. Of course. Find an exponential growth function that models the data. So now I have to identify what I have and what I don't, right? This is the y, this is the function. So it has to be there. If I don't have y, then I don't have a function. This has to be there. Is the independent variable. It's the x normally, but we use t. This is a number. This is Euler's number. It's 2.718. So then what am I missing? Well, I'm missing the original, so A0. Like here, this was called principal. A0 is called the initial number of people or initial mass. So A0, initial or original or starting point, whatever you want to write. So A0, original or initial value or starting point. Whatever you want to call it.
Well, wasn't the starting point 2,000?
Number of people.
Yeah, so it would be 6.
Correct. 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 So this is what I don't have, but of course Amanda is always 10 minutes ahead of me. She does that. That's wonderful. And this I don't have, which is the growth rate. So, okay, growth rate. Okay, now I want to come back to this information. If we are told 2000, 6.04, and 2050, I'm going to copy it because it's on the other page already now for me. Then let's analyze this and see what we're given. What is this?
When x equals 0, it's 6.04.
Right. Thank you, Jeremy. These are two ordered pairs. Ordered pairs. This is what we are given. Two ordered pairs. Awesome. So can anyone again tell us what is the first ordered pair?
0.
Awesome. Thank you. And? Correct. So obviously you already, Amanda, you already plugged this in. But I just want to make sure that everyone understands what we're trying to do. But you're, as I said, awesome. Okay. So this means that when time is 0, A of 0 is 6.04. This is what I want everyone to understand. Can anyone dictate what this means? When t equals 50, A of, careful, A of 50 is 10. This is very important to understand. So if this is the function, if this is the function, the independent variable t, this must be A, the corresponding A of t for any ordered pair. Okay, awesome. So finally we'll go back to A of t equals A0 e to kt. Since I have two variables, I would like us to write two equations. So I would like you to dictate this equation for me and I will write it here.
So
I start here. How much?
A of t.
Which is?
6.04.
Very good. Equals. A0 times E to K, which I don't have, times? Perfect. So how much is K times 0? How much is E to 0?
1.
So therefore, from here, I know E to 0 is not 1. So then I know that A0 is 6.04. As expected. This is the starting point, correct? Is it clear? So I know that A of 0 is 6.04. So when t is 0, when t is 0, A of t is 6.04. So in this equation, I plugged in at the same time 6.04 and at the same time t equals 0. K times 0 is 0. E to 0 is 1. Therefore, A0 is 6.04. I would like us to repeat the steps, but this time for this. Please tell me what to write. Yes, equals. Still keep it at A0 because I'll write it again. E raised to K multiplied by, that's it. That's all I wanted. Is this okay? When time is 50, A of 50 is 10. Of course, I will plug in, because I already have now A0, so this is 10, 6.04 times E to 50K. So yes, we determined A0, which is the initial, the original, whenever we started counting people in that area. The only thing that I have left to determine is K. What do I do? Of course, I have to clean it up. I have to simplify first. That's the mandatory step. 10 divided by 6.04 equals E to 50K. Awesome. Then what? Now I'm ready to. I have to apply something that does that. I cannot just simply say, oh, all of a sudden, let's move 50K in front. I have to apply something to both sides. It's like I'm adding 2 to both sides, or I'm subtracting 10 from both sides. If I don't apply a mechanism, I can all of a sudden say, let's move the power in front. I have to apply the function that allows us to do that. Only this function does that. And I forgot to turn off my phone, so if it rings, my apologies. Okay, so natural log of 10 divided by 6.04 equals 50K. Only this mechanism allowed us to bring 50K in front. Right? It's like the square root of x equals 2. I square both sides to eliminate the square root. And I have to do it to both sides. Right? Okay, and then finally K equals natural log 10 over 6.04 divided by 50. And yes, we have to plug it in the graphing calculator. Ready? Okay. So we have natural log 10 divided by 6.04. Close the parenthesis, and further divide by 50. So for these, either interest rate or growth rate or decay, we have to use 4 digits. If this one is bigger than 5 or above, I have to say 0.0101. So please use 4 digits, decimal digits. So then K equals 0.0101. Now I do have, oops, sorry. I do have the entire model now. 6.04 e to 0.0101t. This is the function. A of t is like f of x, and t is like x. So I have the entire model now. The next question here is, in which year will Israel's population be 9 million?
Equal 9 million. 4A, right?
Exactly. So in part B, this is 9 million. Awesome. First step. Of course. 9 divided by 6.04 equals e to 0.0101t. Again, remember, we must apply a mechanism that allows us to perform the next step. And what is the next step? Yes. Or LOG. I don't want to deter you from using LOG. It's the same thing. It's just easier to write. So the natural log 9 over 6.04 equals 0.0101t, and t equals natural log 9 over 6.04, 0.0101. Yes, I can do this without the calculator. So when you're ready, plug it in. Natural log 9 divided by 6.04. Close the parenthesis and divide. If you want to use the entire number, that's nice. Second previous answer, and I will not truncate. I will get a better approximation. Not that big of a deal. So 39 years. So approximately in the year 2039, assuming the model still holds.
Would we round that up to 40?
You could. I'll accept that. However, if the model is correct, it will start somewhere in the year 2039. In the middle. Okay, I want to add a question here. Question part C. When will the original or initial, which is A0, double? When will the population double? I know we started with 6 million, 6.04 million. When will the population double? What will you say? What will you do? Tell me and I'll write it.
A be 6.04 times 2.
Exactly. 2 times 6.04 equals 6.04 e to 0.0101 t. And you can say, why don't you multiply it? Here's why. Can anyone tell me why I did not multiply 2 by 6.04? I could have. It's not a big deal.
Oh, well, because it would be the exponent.
No? Why didn't I write 12.08 here instead of 2 times 6.02?
Because you're going to get to 6.04.
Exactly. I'm going to divide both sides by 6.04 anyway. So then this is 2 equals e to 0.0101 t. Awesome. Thank you, Wendy. What was the point? I had to divide by 6.04, like we did all the time. So then I apply natural log to both sides. And I will determine when the population, the initial population of 6.04 million people, doubled. Natural log 2 equals 0.0101 t. I keep forgetting to multiply here by natural log e. How come? Because it's 1. Please remember that. Very good. So then t equals natural log 2 over 0.0101. Again, I can't do this with without a calculator. So we have natural log 2 divided by 0.0101 and enter. So roughly about 69 years. But I would personally say in 2068 sometime, assuming the model still holds. Okay, any questions on the exponential decay model? Exponential growth model.
Can we do a decay one?
Yes, of course. Now, do we need another example with the exponential growth? Okay, the exponential decay. Yes, they are the same.
Yeah.
They are the same. Okay, so let's look at problem 16. Problem 16 on page 529. We are given, we are told that an artifact originally had 16 grams of carbon-14. This is just the name. It's not important, but we know it's a radioactive substance. The decay model, again, is A of t, not just A, is 16 e to negative 0.30121 t. It is obvious that it's an exponential decay model because in front of k, which is 0.000121, there is a negative sign. Perfect. Describes the amount of carbon-14 present after t years. Use this model to solve exercises 15 and 16. 16. How many grams of carbon-14 will be, bless you, will be present 11,430 years later. How much? How much will it remain after 11,430 years? What do I have to determine? Yes. Right? The amount, 11,430 years later. Can't do this without the calculator. So
if you just plug that number into t like an exponent?
yeah, that's the time. Yes, exactly. Very good. So we have 16, second and e, in parentheses, please, negative 0.30121 multiplied, you must put the multiplication symbol, 11,430, close the parenthesis and press enter. So the 16 grams will change into 4 after 11,430. As you see, the decay rate is very, very, very slow. Very slow. So 4.0131 grams after 11,000. Of course, I'm going to add a question here. When will the initial mass of 16 grams become half of it? Okay, what do I need to do to see when the 16 will become 8? What do I do? Yes. So this is 16 divided by 2. So I'm going to do exactly what I did before. What will be my next step? Yes. I simplify, dividing both sides by 16. So I have natural log of 0.5 equals negative 0.000121 t. Therefore, t becomes natural log 0.5 negative 0.000121. And we will know how long it takes for this particular type of radioactive substance, carbon-14, how long it takes for 16 grams to be cut in half. Or in other words, 8 of those grams out of 16 disappear in thin air. So what do we have? Natural log 0.5, close the parenthesis, divided by, don't forget parentheses because it's a negative number, or you can put the negative later. But if you want to put it in exactly how we see it here, and then we get 5,728, approximately 5,728 years. You didn't put the negative in the denominator, or you didn't put 0.5 in the natural log.
Oh, you're right. I put 5 instead of 0.5.
Because it's impossible. We know that something is wrong. Time cannot be negative. Okay, this number, 6, for carbon 14, t equals 5,728 years, represents what we call half-life. Is the time needed for this specific radioactive substance. Others have totally different half-times. I'm sorry, half-life, I meant to say. Half-life. Okay. Here's an example that I would like to go through with you. 17. The half-life of the radioactive element krypton-91. Again, the name of the radioactive substance is not important. I'm just I'm showing you a different one that says is 10 seconds. So this is normally denoted by age. So age is 7 to 8 years. So for this one, age is 10 seconds. And this is problem 17. So this second, or krypton-91, second radioactive substance that we are looking at, has 10 seconds. See the difference? 10 seconds and 5,728 years. We cannot even think in those terms. Okay, we have 16, they say we have 16 grams. So our original mass is 16 grams again. So now they're asking us, if 16 grams of krypton-91 are initially present, how many grams are present after 10 seconds? 10 seconds later, A0 is? Another 10 seconds later, A0 is? Another 10 seconds later, A0 is? And other 10 seconds later, 1, because we're asked at 50 seconds. A0 equals 0.5. So in 50 seconds, the 16 grams become 0.5. Extremely fast. Okay, let's look at one more. Unless you need more, and I'm hoping you will come more with more problems next time. On page 530, problem 19. Use the exponential decay model, which now we know it will be given to you. For carbon-14 that we just discussed. And they said that prehistoric cave paintings were discovered in a cave in France. The paint contained 15% of the original carbon-14. So they discovered them, let's say, today, and they measure the content of carbon-14, and it has 15% of the original mass of carbon-14.
So I have a question.
Yes, please.
So if the decay function is the k always negative 0.000121?
The sign in front of k is negative.
Okay, but the k can always be different.
Yes, k is always different. From substance to substance is different. Yes. Now, for carbon-14, the previous, what did we have? For population, we had 0.0101 for right for Israel. For according to the given model, for carbon-14, the K is 0.0121%. So this is different because of the different substance we are looking at. The previous one was with the population was an exponential growth model. So normally population grows, not decays, or it can decay as well. Okay, so here's the question one more time. We have prehistoric cave paintings that were discovered today, let's say, and they measured the still existing carbon-14 in those paintings. And they came up with the conclusion that the paintings still have carbon-14, but they have only 15% of what they had initially. When they were painted, the paint had carbon-14 in it. But because carbon-14 is a radioactive substance and it diminishes its mass in time, today when they were discovered, they only had 15% of the original amount. If I put in 16 grams, only 15% of 16 is still left today. If I put 1,000 grams when they were painted, then today we discovered they only had 15% of that amount. The question now. Estimate the age of the paintings. Now we have to establish what this means. 15% of the original. What does that mean?
Multiply the original by 15%.
Thank you very much, Eric. Awesome. This is what it means, and this is the left-hand side of the equation. Today, when we discovered them, we measured, and they own somehow, and they only have 0.515 of. Remember, the key word here is of, and it has to be multiplication. 0.15 of A0 equals A0e to negative 0.0000121t. Of course, we do not have the original, and we don't care. So, what do I have to do next? Not yet.
You can get out the original line.
We simplify both sides. We don't have it. We don't even care about it. And then indeed, natural log 0.15 equals negative 0.00121t. So one more time, just to make it clear. From this step to this step, I am applying log to both sides. Is that clear? Yes? Yes? No. Sip of water. You don't have any? Ah, I do. Good. Any questions? So how much is it? How old are they? So you divided natural log 0.15 over negative 0.30121, and you got
15,678.
according to this, they are